Are you in the?
I mean, I'm sure someone did from the previous episode, so.
Oh, yeah.
All right, so maybe, okay. I can't select. I can't change the edit on the live feed. So right now the title is monogenoidea. That'll work. I do think we are live. That's good.
We did go through question 4. That's where we left off for the practice. So we went through them all.
I think we were like.
Yeah. Yeah, so yeah, we did homework. And then, yeah, that's it. I said go through and do the homework. And we had R open. Oh. And I figured myself.
Yeah.
Where is our studio?
Well, that's what I was wondering if I turned this on.
Where did it go? Oh, okay, hold on. Of course. I don't know where it went. Where is it zooming? So I see my RStudio. It's off my screen. Let's try this again. It's off the screen. Are you kidding me? What's the shortcut to move? Alt F4? Is that the shortcut to move?
No, that's close. Control tab, I think. Or Shift tab, maybe.
No, Control
Kind of.
Tab. Control Alt Tab.
Alt F4 is like an old school prank to make people close their
No,
windows.
I am looking to capture it and move it.
It's broken. How do you fix it?
No, I wasn't saying.
I don't know where it is. I don't know where RStudio is. It's off my screen. So let's mess with the display settings again. It should be on like screen 3. I don't even know where is screen 1. So where's my cursor? Okay, so there's my cursor. There's 1, screen 2, and then screen. All right, so I've got all of them. And it looks like RStudio is opening up on like a screen 4 that doesn't exist. What on earth is going on here? And I can't get it. Does your guys' RStudio work?
Yeah.
Yeah, ours are working great. No issues here.
This is ridiculous. Okay, so I was going to open up RStudio because it did have some questions about knitting. Let me open up the file.
I did. Yeah, I did.
We're going to start with ANOVA.
Really hard to parse out from all of the words I got. But then when I finally figured out what he's saying to do, I did that.
Let's try this. Let's just
Honestly,
duplicate
there's a bunch of
everything.
different ways that it might happen. You might do it in instead. Go find something.
Yes.
Decided.
You don't know World War II?
This one and no. This one and this one are duplicated. Which
all applied on the front.
I guess that's okay.
We talked about, we talked about a lot.
No,
There were some of
it's
the
the wrong one that's being captured.
I have so
So got something. This is option number 2. Still can't access. That's off my screen. Option 3. I can't get our studio open. I mean, it's open. You can see it. You see it zooming? That's what it's doing on my screen. So when I click on it, that is jacked up.
What is it? Yeah.
I did. I've been closing it and opening it back up for a while. Well, this is almost up. I'm going to do a search. How to move windows. Alt space, Alt tab, Alt space, Alt tab.
Yeah. Feel like a
not from fire, you are involved. Like saying not to apply, almost.
right.
Not to apply those.
Okay. Space. Oh my goodness, I got it. There we go. Get this over here.
Yeah. Oh, yeah.
Trickery. All right. So some of you, at least one of you, said you had issues. Check the top. When you knit to a Word document, this needs to be in there. All right. So if you only had output PDF document, it might not work. All right, especially if you're going for a template. All right. Spacing is important. There is 2 spaces here. One space, one big space, but it's 2 spaces because these are all uniform text. There's 2 spaces there, and then on that next line, there's 2 spaces. So if you're missing spaces, it won't work. All right, so did you do this homework? Did you get it through? Hopefully it was okay. If you had any questions, email me and we can get it fixed. All right. All right. Finally we hit it up. So we finished off the statistical test review. What we are doing now is moving to ANOVA. And unfortunately, as I just said, as I'm looking through this, I didn't do enough. I kind of jumped ahead. I hope you're okay. So, our setup is that we have a data set. We have one categorical independent variable, and we have one quantitative dependent variable. Classic case, you have categories, you have a group, and then you measured something on all individuals in that group. And your question, or you're interested in, is if the means differ between each of the groups itself. All right. classic example. When you have this situation, your target is always to try to do an analysis of variance, an ANOVA. All right, so what we're going to do is kind of start off with this first one. Part one, assumptions are met. We're dealing with two levels. I kind of looked at my next file and said, oh, 3 levels, well, that's 3 variables. No, it was 3 levels, 3 or more levels. So like I've basically finished up what happens when we violate assumptions, but I didn't actually get to the assumptions met yet. So we'll see how we handle that. But we're going to start with a simple one. We have our goal. We know we want to run ANOVA, and in this case, we only have 2 groups. So you've got, let's say, fall versus spring, or you have 2020 versus 2021. All right, just 2 groups. So our goal, or one thing we can do, is an analysis of variance. Now we introduced an analysis of variance now because, a t-test, a 2-sample t-test, it would have probably addressed this issue, this one categorical variable, one dependent quantitative variable where we have only 2 levels. A t-test is simply a special version of an analysis of variance. All right, it's a special case when we only have 2 levels. What analysis of variance is doing, it's going to compare the variances. It's going to utilize the variances within groups and between groups to determine if the group means differ. All right, so that's kind of the important part. I've had numerous people throughout the years say analysis of variance is comparing if the variances are equal. No, it doesn't. It utilizes the variance to inform us if the means are different. So how does it do that? Well, the variances that we're going to look at is the variance within a group and the variance between the groups. So collectively, I've split this out as a signal and a noise. All right, it's a signal and a noise. So the within groups is the noise aspect of it. This is all of the error. This is just the random variation that we have when we collect our data. All right. This is called a sum of squares error term. We are basically looking at overall variation of our data points. Overall variation of our data points. So the more our data points vary, the larger this value will be. The between groups is a signal. Now we're still looking at the variation. We're still looking at the variance. But instead of looking at each of the individual data points, we're looking at the variance of our points to the overall grand mean of our data. All right, so the ones looking at this within groups, this noise is the variation within each of our groups. How much does our data point vary within each group? This, the between groups, is looking at how much variation do we have compared to a grand mean, an overall mean. This between groups gives us our signal. The within groups is our noise. If the noise and the signal are equal, then we can't really detect any differences between the groups. But the more the signal exceeds our noise, our error, the more likely it is that our means are going to be different. Now, we do this by calculating these terms, sums of squares. So we have a sum of squares error term, we have a sum of squares treatment term, or as we add additional variables, you're going to have a sum of squares treatment, maybe sum of squares time, sum of squares drug interaction, who knows? All right, we can add each of them to our data point. But these sums of squares follow the same sum of squares that we've learned when we calculate variance. That property is that as we increase our sample size, the sum of squares are gradually increased. So what we're going to do is take the average by dividing by our degrees of freedom to get a mean square term. So the average sum of squares, basically. All right. The degrees of freedom that we're looking at varies. So the error is our sample size minus the number of groups that we have. Our treatment degrees of freedom is the number of groups that we have minus 1. All right. The degrees of freedom of the error plus the treatment will equal our total sample size minus 1. Interesting property. Right. Just like sum of squares of our treatment plus the sum of squares of the error will equal the sum of squares total. These apply. These are true, the mean square terms don't. So like the mean square of your treatment plus the mean squares of the error does not equal the mean squares of our total. We're going to use our mean squares treatment and divide it by the mean squares of the error to generate our signal to noise ratio. And in this case for an ANOVA, that is our F statistic. All right? So if our signal equals to noise, then that ratio is going to be equal to 1. And that tells us that there's no difference in the group. As our signal becomes larger, as we get more differences in our means, then this relationship, MS treatment to the MS error, is going to start to exceed 1. We'll get to a point then where it's so large that something other than chance is producing that difference. So this is kind of how it's working. And I grabbed this off of a website. I think it's in PDF. Oh, hold on. Ooh. Darn it. So whoever's watching just didn't see anything on the screen. Catch that. Alright, hold on. Man. This is ridiculous. Maybe? Let's figure out where I can get this. Three. Display 2. Try that. Definitely not display 2. Display 3. Okay. Which now you guys can see that. What the heck? Oh no. Okay, so that worked. No. So I lost everything again. Are you kidding? Hold on, no. There it is. There it is. Hold on. That's up. This is ridiculous. We're gonna do something different. We're just gonna have to switch this. All right, I'll have to contact IT because this is not working right. Still continue. All right, so this is what ANOVA is doing. This is what ANOVA is doing. So we've got sums of squares treatment is looking at our group mean. So each of these is a group mean. Red is group 1, that's our mean. Green's group 2, blue's group 3. Our treatment, sums of squares treatment, that signal is how far away are we for each of these groups compared to that group mean. And it's weighted. It's a weighted mean because we have all these different values inside of our group. All right? So as our means start to differ, we're getting a larger difference. Our means are going to be farther and farther away. Our error term is strictly within each group. That's our variance within each group. All right, so we're not ANOVA is testing if the means are equal, but it's accomplishing that by using different variance measures. All right, different sum of squares measures to calculate our mean squares terms. All right, so that signal to noise ratio is this: mean squares treatment over our mean squares error. So if our assumptions are met for ANOVA, then this F will follow an F distribution, and it has the F distribution is defined by 2 degrees of freedom, dF1, dF2. What are those degrees of freedom? It goes back to our mean squares terms. Mean squares treatment has a degrees of freedom treatment. That's our numerator. The denominator is the mean square error term. That had the degrees of freedom. That's our degrees of freedom number 2. So our F distribution has infinite number of curves. All right, so we need to know what our degrees of freedom are to generate our p-values. Now, if our assumptions are met, we can just go right to that actual curve of the F statistic to calculate our p-value. And our p-value then is that area under the curve to the right of our actual observed F statistic, F observed value. Right? If this area is greater than 5%, then we fail to reject our hypothesis. If it's less than 5%, then we conclude that something other than chance gave us our difference, and that something other than chance is the group classification. It's our categories that we're working with. So, what are these assumptions? We've got 3 assumptions of analysis of variance. Assumption 1, data are random and independent. Assumption 2, data are normal within each of our groups. Within each of our groups. That is this. Within each of our groups, within the red group, these data are normally distributed. Within our green group, data are normally distributed. Within our blue group, data are normally distributed. All right, so we're going to have to do multiple qplots to investigate that assumption. And then number 3 is that our data are homoscedastic, meaning we have equal variances. The variances in each of our groups is equal. All right? The alternative of homoscedastic is heteroscedastic. All right, so what are we going to use? We're going to use the CAR package. That's for our, we're going to use that to generate our ANOVA tables, also to do our Qqplots and the Brown Forsyth test. We're going to use the multcomp package. It's a multiple comparison package. All right, and then our data sets will be ClassLength.csv, and we're going to use the cabbages data set. Cabbages, I don't think it's being used in this data set, but or in this presentation, but I could be wrong. The cabbages is in the mass package, so may need to load the mass package, or we can actually load the data set without actually loading that mass package in there. Does anyone know how to do that? Maybe?
The global environment?
I don't know if there's a way to do it that way. I'd say no.
Okay. Oh, yeah.
There's a function called data.
There's a package mass.
There is, yeah, so load the package mass and then you have access to it. But what if we didn't want to load the entire mass package?
Why would you, I'm sorry to interrupt, but why would you not want to do that?
For us, probably doesn't matter. But like you go on and you're doing some big memory intensive programming, you're trying to minimize how much memory R is using so that you can dedicate all of it towards algorithms and the generation or the analysis that you're doing. So like if you're doing like Bayesian trees or whatever, yeah, you might want to save as much memory as you could, which then, yeah, let's not load the mass package, let's just grab the data set. So the way we can do it is use the data function. Open up. Where's my cursor? It is. So if I just go over to the help file, you can see it. Just type in data. Question data. DataSets. Here it is. So DataSets function. We specify where the package or what package we're using. So if we wanted to load the cabbages without loading the mask, it could be as simple as just saying data, cabbages, and then package equals mass. And then you can see it, it's listed as promise because it's in memory, it's ready to be used. I don't think the memory is actually being allocated until you access it the very first time. So as soon as I click on it, now it appears. So, easy way, but again, why would you do that? Anything that I do, I'm not trying to save memory. All right, so here's our first situation. All right, we've got several experimental treatments. All right, we made a measurement on something. All right, and then we asked, does our something vary by treatment? All right, so we collect our data. The first thing we want to do is make a visual display, make a graphical display. Now, typically that's going to be a plot of our means and then standard error or standard deviation. I prefer standard error. All right, typically that's what it's going to be. But a simple way in R is just to generate a box plot. Right, so a box plot is going to graph the median, it's going to graph the interquartile ranges, it's going to show your 1.5x or the spread of our data points. So this is a box plot of vitamin C as a function of culture for the cabbages data set. That works. And I have the second one here, which is interaction plots. We're not quite there yet, we'll come back to it. But this is a simple way to do it in R and gets us started. Is this publication quality? Could be, it could be. But if you're interested in comparing means, I don't think it makes sense to do a box plot that's showing medians. So for that, we kind of go back, use the aggregate function, calculate your means, use the aggregate function, calculate your standard errors, and then take that over to Excel or Google Sheets and make your figure that way. That's probably that's my recommended approach. All right, and that's kind of why I listed here. So make the Excel graph, you just use R to do the aggregate function to get everything for you, and then make it right in Excel. And we'll come back to the interaction plots. So what we're going to do is we're going to work with class length.csv. This is technically a made-up data set, but this data set is basically the length of class for each day of the week. So let's say last year I went through and I recorded how long I talked on Monday and how long I talked on Wednesday. Question being, was one class always longer than the other? All right, that's the idea. So go ahead and download class length.csv, read it into R, all right, and I have it read in as class length, all lowercase, all one word. What we'll do is we'll work through it. So kind of things I want you to do, things that we're interested in is first look at the data, kind of come up with like questions. What are we going to be asking here? And then we'll proceed and kind of walk through how to do this, how to analyze these data. So at least start and try to generate a display.
wondering if you could help me with it. Could you tell me whether I can't put the cabbages in? Whether you did it?
Oh, really?
Yeah,
Let me
that's
see
right.
here. Transcript R data. I'm gonna downloading these files so I can.
No worries.
All right. So you had problems with that?
Yeah, so the data cabbages.
No quotes around cabbages. You need the quotes around mass. So no quotes around cabbages, but you need the quotes around mass. All right, did you get it in? Did you make a graph? Simple box plot, hopefully. So, first thing up is I just inspect the data. That's what I do. Made a box plot, just plot. Again, just do plot. Y is a function of X is data, and data frame. So in this case, it would be time is a function of day, data equals class length, and it'll generate a box plot. Pretty simple. All right. But again, I don't really prefer it, so what I like to do is to pull the mean and the standard errors using the aggregate function, and then transferring that into Excel or some other program. All right. So that's what I did with that. So I have the mean, got the means for Monday and Wednesday. I have standard errors. I made a plot where it's the points, and then spread is the standard errors, plus or minus these things. All right. So I look at it. Now I know, my initial question was, does class length differ between these 2 days? I look at this. I'm not going to be surprised if the p-value is greater than 0.05. Just no. All right. So, here's the script for it. How to do it in Excel. I did this in R actually. So, script's available. If you're trying to do this and you run into some problems, please come talk to me. I can help you out, no problem. I can help you out. But I kind of had to do a loop in order to get our standard error bars and the whiskers and so forth. I can show you how to do that. All right, so we looked at it. I'm not going to be surprised if I don't find a difference, but I still want to run the test. So the question is, what test do I run? Well, our starting options is to run a t-test or an ANOVA. Now, I've been conditioned, and I think a lot of people are conditioned to say, I have 2 groups, I'm just going to run a t-test, which is fine. T-test is simply a specialized version of ANOVA that we can use if we have 2 levels in our independent variable. I actually like ANOVA because we can partition the variance into the different groups. And then we could actually say, you know what, we have a difference, I can then say X percentage of the variation in our data set is due to this group classification. ANOVA allows us to do that. And it's one step. Are you going to get different answers? No. You'll get the same answers. You'll get the same p-values. All right, so we can do one or the other to compare the means. All right, so students t-test is the full name for it. It's a regular 2-sample t-test. Why is it called students t-test? Was it created for students?
The last name of the person discovered, right?
It is the last name of a person. But was it his actual name? No, not.
Just guessing here, so.
No, you're right. It's a pseudonym. Pseudonym of the actual author of the paper that introduced this. A period student. Who's the guy? Alex, do you remember?
Was he a brewer?
He was a brewer.
Wow.
He was brewer at Guinness. Yeah, they kept you tight on there. You couldn't do it. So yeah, and William Gossett wrote it, came up with it, had it published under a pseudonym. So it was students t-test. But yeah, see, beer makes the world go round. All right, so students t-test is testing if the means are equal. Our null hypothesis is that the mean of group 1 is equal to the mean of group 2. And again, it goes back to this whole idea in the theory of hypothesis tests. We assume that all of our data came from the same population. All right, if they all came from the same population, then these groups are just random samples of it, and their mean should be equal. That's our starting point. That's the assumption that we make. All right, that we can reject based on probability theory. Our alternate then is that they're not equal. But since we have two groups, we don't have to stop just at they're not equal. We could actually say group 1 is larger than group 2. Or we could say group 1 is smaller than group 2. All right, that's all just going to be like a priority examples. If we know that one should be larger, we can start with that. But if we don't know that it's going to be larger, then it's probably best just to go ahead and say there's no difference is our alternate hypothesis. All right, so our assumptions are going to be the same as the ANOVA. Data are random and independent. Our data are normally distributed within each group, and our variances are equal. All right, so how do we check this? Well, for the normality assumption, we use qqplots. We're going to use qqplot to look at our groups. And what's been nice is that new versions of the CAR package allow us to do the qqplot by writing a function. Y is a function of x. And qqplots then will create a qqplot for every group within our independent variable. Now, if we weren't going to do that, if we didn't have this, the old way was to create subsets. We had to do a subset for every single group and then do a qqplot on that subset. We'll learn how to do subsets a little bit later, but for now we're going to make use of the power of R and use the qqplot function. All right? So what we're looking for is serious violations of normality. All right? Moderate violations, no big deal. ANOVA is going to be robust to that. All right? If we're skewed, then both should be skewed in the same direction. So when we do our qqplot, if we have curved, let's say a curve that goes up, say like this, then that other group should be the same way. Should have the same shape. Right? If they don't, if they're opposite shapes, you can't do it. You can't make that comparison. The third assumption is the equal variance assumption. And this is the important one. All right? Because if we're going to utilize our variances to determine if the means are equal, then our variances better be equal themselves. All right? How are we going to check that? Well, we're going to check that using either the Brown-Forsythe test or the Flickner-Colleen test. Which one we use depends on our conclusion for the normality. So if we have suspicion that our data are non-normal, or we know for a fact that we're non-normal, then we run the Fligner-Collin test. If everything looks great, everything looks normally distributed, we're going to run the Brown-Forsyth test. All right? If all of our assumptions are met, then we can just go ahead and run a t-test using t.test function. And that t-test function takes, you could write it in different ways. I'm going to show you how to use the formula. So what we're looking at with the formula is we're testing if the means of y differ for each of these groups in X. We pass the data frame so that we don't have to use their data $ variable name, and we specify var.equal equals t. All right. If var.equal equals false, then that's a Welch's t-test. And we'll talk about that when we violate assumptions. All right. So students' t-test are normality check. Preferred method is qplot. I say our old method used to be subsets, and this is how we do it. So the subset function is to take a data frame, pull out all of the rows where some variable that we're interested in matches some category, and this function, subset function, returns a data frame. All right, so then we take that data frame, here's a data frame, we use our $ to reference a variable within that data frame itself to make our qplot. So just for kind of examples, this is how I would have done it the old way to check the assumptions in this data set. All right. First, I figured out what my levels are. So that's all the way up here. Let me just move mark down over here. But all right. So checking normality the old way. Levels, class, length. All right, so I'm running this. I need to know exactly what levels we're dealing with because this subset function needs the exact name, exact capitalization, exact spacing. If you read in your data incorrectly or you typed in your data incorrectly and had, let's say, a leading space or an extra space, it'll show up in this list. So maybe you have Monday and then Wednesday, Wednesday, Wednesday. Where you have on one of the Wednesdays, it's like this. On another Wednesday, you have a space before it. And then on another Wednesday, you have a space after it. Those are all different levels. Kind of tells you, hey, I need to go back and fix this. So I know my levels, and now I'm going to do my qplot. So qplot, I need a variable. So the format is going to be our data $ variable. Right? And the variable that we're looking at is time. We want to do a qplot of our time. But I can't use class length. So I can't do this. Not because it won't work. Let me load my packages. I mean, it will work. If I run this, it'll make a qplot. But our assumption isn't we're normally distributed within that one variable. We're normally distributed within each group. So if I had two groups, and each group is normally distributed, but they're located at two different x's. Here's x bar 1, here's x bar 2. If I did a qplot of our data set and ignored this, we're going to look something like this. And you're going to say, well, that's non-normal. Yeah, it is. It's non-normal. But that doesn't address the assumption. Are these normally distributed within each of our groups? So this doesn't work. And this is where the subset function comes into play. So we want the subset. And again, that subset function is going to return data frame. So that subsets, we can use the $ notation on this. So what we're looking at is subset of our day length, or class length, where day is equal to, double equal sign, and then we have to have quotes, and we have to give it the exact name of our levels. So Monday. That's going to work. And I'm going to copy that and paste this and change that to Wednesday. And when I run the chunk, then I get two graphs. This is Monday's data set. That looks normally distributed. This is Wednesday's data set. That looks normally distributed. All right. So this took 3 lines of code. 1 line to figure out the levels, 1 line to do the qplot for Monday, 1 line to do the qplot for Wednesday. Is there an easier way to do it?
Yeah.
Yes, there is. Qplot in the car package will allow us to create a qplot for each level of our independent variable. I write it as a formula. And qplot is going to say, okay, here's the formula. I'm going to look at day, and then I'm going to do the subset for you and return an individual plot for each of our levels. I run this. I get both graphs all at once. Didn't have to bother with subsets. I didn't have to worry about the levels, figuring out what I called them. Right? It works. Downside of this, especially in a markdown document, sometimes it makes the graphs really small. And it's hard to say. Then you have to kind of like enlarge them. If that's the case, then sometimes it's best just to go down and take this command, copy it, and then try in the console. And then you open it up in the console and then kind of resize this, make it bigger, then try to view some of those. Fortunately for this class, we're not going to have a huge number of groups, so hopefully we don't have to get to that problem. Did it work? qplot work?
Mm-hmm.
Right. All right. So we did. Yeah, these are the curves. This was the qplot, and just point out it's the new version of R. So if anyone took stats 2 years ago, and right, if you didn't upgrade, it's not going to work. So make sure it's upgraded. And that came out this fall. So it's pretty new. All right, so normally distributed, we now check our next assumption, which is equal variance assumption. These tests, both of these tests, Brown-Forsythe test and the Fligner-Killeen test, have the same null and alternate hypothesis. Our null hypothesis is that all variances are equal. The alternate is that at least one of the variances differ from the rest. And in this case, we don't care which ones are different. We just need to see, are they the same or not? All right. Test choice depends on normality of the data. So in this case, our assumptions are met. So we're going to run the Brown-Forsythe test. All right. This is found in the car package, and it uses an actual different name. It uses a Levine test. Levine test is a test of equal variance, but it centers everything on the means. It's not quite as robust slight violations of normality as the Brown-Forsythe test, which centers on the median. So when they created the package, they said Levine test and Brown-Forsythe test are basically this exact same. It just depends on where they measure the variance from. Is it from the mean or is it from the median? So in order to access Brown-Forsythe, we're going to use the Levine test and then specify center equals median. Now, nice thing about this is that this is the default. So if you forget to do center equals median, it will automatically do a Brown-Forsythe for you. But I just like including it in because it just reinforces that, yeah, I'm doing a Brown-Forsythe test. And you set it up just like the same formula as we did for the qplot. Y is a function of x, or data from. Fligner clean test is built-in package, or it's built-in function. We use that when the data are non-normal, or if we have suspicions that data are non-normal. All right. The function for this is Fligner.test, and we pass it a formula. Y is a function of x. Again, y is our dependent variable, x is our independent variable. So for us, class length, we are using Brown-Forsythe test. And this is how I run it. So Levine test, time is a function of day, data equals class length, center equals median. We get the output. So what does this tell us? Yep, yeah, variances are equal. What were the important ones to look at? Important values to look at? The F statistic. This F value is our test statistic. Test statistics, very few exceptions, report to 2 decimal places. It reports degrees of freedom, 1 and 48. There's 2 values there because it follows an F distribution. We need to report both. And then our p-value. P-value is greater than 0.05. We failed to reject their null hypothesis. Therefore, our variances are equal. So, just write up variances are equal. Test name, Brown-Forsythe. F statistic, 2.76. I put our degrees of freedom as a subscript here. So 1, 48. And then I report the p-value. So everything looks good. All assumptions are met. So now we just perform our test. And our test in this case is t.test. That's our function. And we pass it the same formula that we've been using to check the assumption. So time is a function of day, data equals class length, var dot equals t. And we get this output. And the output tells us we ran a 2-sample t-test. It tells us our test statistic t. Gives us the degrees of freedom, 48. Gives us our p-value. These are all things that we have to report. All right, so we report our conclusion or interpretation. We report the test that was run, test statistic, degrees of freedom, p-value. We report all of those. So in this case, length of classes is equal between the days. All right. You good? All right, so basically did the analysis. We know our conclusion. Now it's time for that full write-up that we always try to do. Real important for all of you. So my write-up, an example of a write-up could be this. We investigated if the length of statistics class differs between the Monday and Wednesday class. Quantile plot suggested data are normal, and Brown-Forsythe showed homoscedasticity. Test statistic degrees of freedom p-value right there. The t-test was used to compare the means, and the test showed that class length was similar between the 2 class days. I listed my t-test statistic, 0.19. I gave the degrees of freedom as a subscript here, 48, and I gave the p-value. So do we need a post-hoc test?
No.
Why not? What's that?
That I don't know why you said that. But I would assume it's because our data was.
Because they're what?
Our data was almost acid. Right?
Well, they're homoscedastic. That allowed us to run the t-test.
Our p-value was far enough away from
Our p-value, okay, p-value is large enough. So what do we conclude?
Well, it was just our p-value was different enough from 0.5 that we didn't need a posthoc test.
Yep.
To verify.
So to verify what?
The main factor difference.
To verify our initial results.
Yeah. So why did we run a posthoc test? To determine which ones are different, right? In this case, they're not different, so there's no posthoc. And even if we got a p-value less than 0.05 where we conclude that they are different, do we need a posthoc? No, because there's only two groups. We look at the means and can easily say, oh yeah, they're different. This one's larger than that one. Difficulty comes when we have more than two levels. Now we run our ANOVA and we get a difference and we say, okay, yeah, the means are different, but we don't know which ones are different. We can look at all the means and we can say, yeah, this one's the largest and this one's the smallest, but we don't know if those are the two that are different. Maybe all of the means are different. Maybe it's just the largest and the smallest that are different. All right? So in a two-sample test, in a t-test, in a two-sample or a two-level test, we don't need a posthoc. If there's a difference, there's a difference. We just look at the value and we can easily say this one's larger, this one's smaller. All right? So we have our t-test, we have our p-value, we have that conclusion. What if we wanted to run an ANOVA? Well, steps for doing an ANOVA are a little bit different. So in R, what we do first, what I encourage you to do first, is to first create a linear model of our data. Right? We create our linear model, and then we pass that model onto another function that would generate our ANOVA table. Now, we don't need to do that. We don't have to do this. But my recommendation is to do it this way, because as we add additional variables, this is how we run our two-way, three-way, multi-way ANOVAs and ANCOVAs and mixed effects models and so forth. So just kind of get used to making a model and then generating our ANOVA after. So how do we make the models? For this, we're doing a linear model. A linear model. The function is LM for linear model. And what we're doing is creating a function, creating an equation that best predicts y based on the levels of x. Right? This quote, I just copied and pasted it right off the help file, because that explains exactly what it's doing. It's used to fit linear models. It can be used to carry out regression, single stratum analysis, variance, and analysis of covariance, although AOV may provide a more convenient interface for these. Yeah, it may be more convenient, but if you know how to make a linear model, then everything else, no matter how complex your data set is, you can analyze. All right? So we're going to create our linear model. We're going to save it as a new object. Once we have that new object, we'll then pass it onto the ANOVA function that's found in our car package. Now, there's a lowercase ANOVA and there's a capital ANOVA. The lowercase version is in the base package. Uppercase ANOVA is in the car package. My recommendation is always to use the car package. For a one-way ANOVA, doesn't matter. As we add more variables, it can make a difference. And we'll talk about that. All right? So, our hypothesis, not quite, these are kind of right. But for this situation, we only have two levels. So our null hypothesis is that the mean of group 1 is equal to the mean of group 2. If we had three levels, the ANOVA null hypothesis is that the means are equal. We have four groups. The null hypothesis is that the means are equal. All right? Our alternate hypothesis for an ANOVA is that the means are not equal. All right? In a t-test, we could specify direction. ANOVA, we don't do that. We don't specify direction. They're either equal or they're not equal. All right? So, Class length. Back to our class length data set. ANOVA has the same assumptions as the t-test. We've already checked it. No point in rechecking. All right, so we're just going to jump right into how to construct this ANOVA. So as I said, we're going to first create a linear model. And what I did is I created the linear model and I saved it as the object called mod, M-O-D. So I created my linear model, time is a function of day, where those are found in the data frame class length. And then once I've created the linear model, I pass that model to the ANOVA function. And that produces our ANOVA table. All right, so kind of run it, make sure you get this table. It'll work, hopefully. All right, so this is how we do an ANOVA. Real simple. We've got our F statistic, F value, that's our test statistic. P value, right there, 0.85. Our degrees of freedom, 1 in 48. And if you compare it, this is the exact same P value as our t-test. Different test statistic, different degrees of freedom, same P value. Now, what about these? Remember the treatment and the error? Treatment, day, that's our sum of squares term. The residual, that's our error, 1303.84. Right? These are both sums of squares. We have to take the averages by dividing by their degrees of freedom to get the mean square values. Our F is the mean square of our day divided by the mean square of our residuals, our signal to noise ratio. In this case, our signal to noise ratio is really, really small. So our noise basically swamps the signal. There's much more variation within each of our days than there is comparing the means to the graining. All right, so what's our conclusion? What's our interpretation? Are the means different? No. Same answer. Same answer that we had with our t-test. All right, I think what we're going to do is I think we're going to stop. No, we'll continue because we're almost done here, and then we have practice. All right, so review. Or actually, we have our model. One of the other things we can do is actually look at the summary of our model. And we're going to do this more as we add additional variables to our analysis. All right, so it kind of gives us a bunch of different stuff. Gives us the model call. It gives us residual information. All right, this residual information kind of gives us an idea about whether or not our assumptions were met. All right, because if all of our assumptions are met, then our residuals should be normally distributed. And what's a residual? It's the distance of each of our data points from our predicted equation, or predicted line. We'll talk a bit more about that. Yellow lists all of our coefficients here. Our intercept. This is basically giving us the equation of the best fit line. Right? And again, we'll talk about these. For us, we're mostly interested in these two, the blue and the red terms, for a regular simple ANOVA. That's typically what we're interested in. The red is the same information that came from that ANOVA table. All right. So for a simple ANOVA, this matches. We've got our F statistic, 0.03608 on 1 in 48 degrees of freedom gives us the p-value. Incidentally, since this is a two-sample ANOVA, that p-value is the exact same p-value up there. All right. What about the blue? The blue kind of tells us about some model fit. Remember when I said how much variation in our dependent variable is explained by our grouping? That's what these R squared are. So R, multiple R squared term, 0.00075. Less than 0.1% of the total variation class length is due to days, due to our class day. Now, as we start getting differences, maybe you'll get a really small p-value, but day only accounts for 15% of the variation. There's still a lot more variation out there that we could try to explain. Even though we have a difference, there's still a lot more that we don't know. And what we'll do is with the coefficients, it breaks it down into only intercept and day Wednesday. So why is that? Because we only had 2 levels. We got Monday and Wednesday. What this typically does is take our level alphabetically and put the Mondays at the intercept. So if we did our aggregate, go back several slides before and look at our average for Monday, you're going to see our average is 78.08. That's our average. And then our average for Wednesday is 0.28 units less than the intercept. So what our t-test does is, hey, is this difference, this negative 0.28, is that equal to 0 or not? That's what our t-test does. So those of you that had the grad stats, t was the difference in our means divided by their standard error. Yeah, there's our difference. That's what our t-test is testing. That's our test statistic for the t-value. That's the p-value from our t. So that's all that's doing. Now it becomes a little bit more important when we have 3, 4, 5 levels. All right, we can kind of judge how different is everything to that intercept, but that's not really a great way to figure out which means are different from each other. All right, so ANOVA versus a t-test. They both arrive at the same conclusions. There's no difference in this case. All right, and they had the same p-values. So if they have the same p-values, why would we choose one over the other? Well, ANOVA's benefit kind of comes down to that partitioning of the variance. We can separate it out to the error variance and the treatment variance, and then we can apply like percentages. X amount of variation is accounted for by this category. All right, or hey, we have X percent that we didn't know, that we can't explain yet. All right, maybe that's important to report. So that's one of the benefits. And second benefit is it seems to be a little bit more robust to violations of our assumptions. A little bit more robust, especially in terms of normality. That's just kind of why I tend to prefer the ANOVA. But again, p-values end up coming out to be the same thing. In this case, we don't need a post-hoc test because we only had 2 levels. If they're different, we just look at the means and say, yeah, one is larger than the other. All right, so what happens if we violate any of these assumptions? If our data are non-normal, we're usually okay to continue with an ANOVA. It's usually robust enough to continue with it. Unless it's like really non-normal, then you probably want to see about fixing it or choosing a different test. If we have unequal variances, then what you're going to do is a Welch's t-test or a Welch's ANOVA. I'm going to show you how to do Welch's ANOVA a little bit later. Welch's t-test is as simple as changing this. var dot equal equals f. That's all you need to do. And that does a Welch's t-test. What if we're both non-normal and heteroscedastic? Probably do some randomization tests. And again, I'm not going to present them here. We'll present them with a larger ANOVA because it all forms part of doing pairwise tests as a post-hoc tests. All right, so these are the same exact choices as if we have more than 2 levels. All right, so what we're going to do is kind of jump to that case where we have 3 or more levels in our classification. So let's say we had 5 days of classes. Let's compare class days, Monday, Tuesday, Wednesday, Thursday, Friday. We can't do a regular t-test at that point. Right? We've got more than 2 levels. So we'll address these assumptions, or those violations later on. All right, so for Wednesday, we've got Gqplots.csv. Faculty raised fancy guppies for the intro bio labs. Fish were raised in both cabinets and Science 3. So what you did was went to the different aquaria and said, hey, if they were raised in a certain building, does that have an effect on their overall size? So download the data set, check your assumptions, run your test, have a write-up. We'll talk about this on Wednesday and kind of review it. Just kind of as a trial run of checking your assumptions, seeing if everything works. All right. All right. I'm gonna apologize for this. This live stream sucks. So you gotta record the actual presentation. But I'm gonna head down and open up a ticket with IT. All right. We are done.